teacher. I hope that you are going well. I give my grades to you. I hope that we're having a good day. So today we are going to introduce the exam of the partial 3, and I want to explain the things that I choose and made in this part. I like the example of the partial 2, and I want to do the same way to explain two problems like the engineering and the science. We will see this, but I want to say to you that I want to do that in that formula because I want to understand more, and that makes me feel good because I learn more in that way. So we need to start. And what we'll cover? Well, the objective in here, like I say, is the two problems that we need to see: the engineering and the science. And this helps us to understand why these problems helped. Like in engineering, most of the people don't see this important. They feel like it's only a problem of calculus and I don't care, I do like my own way. But the things that I see in this subject is that this is important to understand. This is important to make a reflection, and this is the why I choose the engineering and the important the science, because the science is very interesting. We have the results, the interpretation, and more. So the key points, the key things that we introduce in here is the derivative, the instantaneous velocity, the sum and difference rule, the first-step process, power rule, and critical value. These are the important things that we need to understand. So, we need to start engineering the derivative as instantaneous velocity, rocket ascent, and analysis. Well, we have the problem here. Problem statement. A mechanical engineering team launched a small research rocket to test a telemetry sensor. The rocket's height above the ground, S of t meters, t seconds after launch is modeled by S of t equals minus 4.9 t to the square plus 58.8 t plus 1.5. So we have the ABC. We need to find A, the instantaneous velocity function, B of t equals C prime value of t, using the first-step process. B, the velocity of the rocket at t equals 2 seconds and at t equals 8 seconds. The C, the time at which the rocket reaches its maximum height, B equals 0. So we have here the solution for step process. For the step 1, it's like we say S of t plus h equals minus 4.9 to t plus h to the square plus 58.8 to t plus h plus 1.5. So that's for the step 1. For the step 2, s of t plus h minus s of t equals minus 9.8 th minus 4.9 h to the square plus 58.8 h. For the step 3, s of t plus h minus s of t divided by h minus equals, h equals minus 9.8 t minus 4.9 h plus 58.8. Where's the step 4? Well, we have here step 4. This is important. V of t equals to the limit of h approaches 0, in parentheses, minus 9.8 t minus 4.9 h plus 88.8 equals minus 9.8 t plus 58.8. We have the results here and the interpretation, but I want to explain first the interpretation to understand more. The rocket climbs with decreasing speed as gravity acts on it. Momentarily it stops at t equals 6 seconds, reaching its maximum height of s of 6 equals minus 4.9 of 36 plus 58.8 of 6 plus 1.5. That's gives us an 177.9 meters, and then falls back with a negative downward velocity. This is exactly what engineers use to schedule sensor readings and parachute deployment. So the results are here. For A, have that equals 39.2 meters seconds. At t equals 2 seconds, the rocket is still climbing rapidly. And for B, the formula we have in the part of here, B of A equals minus 9.8, that we see that we already see that. So the result of that equals minus 90.6 meters seconds. And for C we have the seconds, t equals 6 seconds. So that's the problem 1. Since there is no, because I want to, because in this part explain us to why the engineers use these like schedule sensors, readings and parachute deployment. This is interesting already to understand why, like what seconds maybe this could happen. And oh wait, I maybe want to calculate this in the PC, and I want to do this. I start to plug it in the keyboard, and we have the result. We have meters of seconds, maybe the part 1. When this gets at 2 seconds, we have the result, and when this gets at 8 seconds, we have the result, and the velocity is 0, and the apex we have the 6 seconds. And this, well, we have the problem of science, basic differentiation rules, material culture rate, bacterial. We are going to see bacterial. Problem mistake. microbiology lab is monitoring a bacterial culture growing in a controlled molecular solution. The population N of t thousands of cells. T hours after inoculation is modeled by N of t equals to 3 to the cube minus 21 to the square plus 60t plus 40,000. Well, we need to find ABC, the growth rate function N of t and prime N of t, using the power rule and sum divided by difference rule. B, the growth rate at t equals 1h and at t equals 3h. C, the critical times when the growth rate is 0 and prime N of t equals 0. So we have here the solution. For the first step, power rule, d by dt to 2, 3t to the cube equals 6t squared, and d by dt in parentheses minus 21t to squared equals minus 42 t, and d divided by dt. Oh, we have the numbers that we explained before. So we only put that numbers in the form. So the step 2, sum and difference rule, and prime of t equals 6t to the square minus 42t plus 60. Step 3, factor to find critical values. 60 to the square minus 42t plus 16 equals 0. And to t to the square minus 7t plus 10 equals 0. 2t in parentheses t minus 2 and t minus 5, that gives us 0. So the critical times, t equals 2 hours and t equals 5 hours. We have the result and the interpretation. Here's the interpretation. For the culture grows quickly during the first 2 hours, then enters a temporary decline, likely from nutrient depletion or a buildup of waste products between t equals 2 hours and t equals 5. Before adapting the growth again after t equals 5 hours. Researchers can use these to time nutrient replenishment or harvesting. This is the important thing, no? Researchers can use these to time nutrient replenishment or harvesting. So we have the results to A that equals 24,000 divided by H. So here the culture is growing fast in the first hour, and B equals minus 12,000 divided by H. Here the population is declining between t equals 2 and t equals 5. 2 equals 2 hours and 2 equals 5 hours. And here growth rate switches direction at these times. So this is important to understand the population living in the country or in the world. But we can predict the things here. For the conclusion, like I say, I like this formula that I do in the second partial, and we make the third partial like the same way, but with another problem from the section 2.4 and then 2.5. So I choose this because like I say always, I understand more the topics of it, because we introduced now the derivatives, and this is important. So this gives us a more more concerned to understand more the topics, but we need to put in a program. Normally the people give us a program because I understand more, and when we get an opportunity in a job, and the client gives like, oh, I want to program to calculate this when the population gets higher and other things. We need to understand, we need to know the formulas, the things, because when we have the formulas, we need to introduce, translate to a program in the computer. So it's more than know in the whole brain, because we need to understand it. We need to make it easier to the client, to the user. And this is for me the conclusion. This is for my part all of this. And thank you for put attention. Thank you for this time, for seeing this video, and I hope that we can learn together, understand more the topics. And this is all for me. Thank you for the attention, and maybe we are seeing us for the next time. Thank you.